So in the next step here, we calculate how much energy is released when we combine hydrogen gas with oxygen from the atmosphere to form water molecules. So we take 2H2 plus O2, both in gaseous form, and we're going to turn it into 2H2O in liquid form. This will give us the higher heating value of burning water using this method. The higher heating value is all the energy you get out of the combustion, including after the vaporized water has turned back into a liquid. So for H2 and O2, both are 0 kilojoules per mole. For 2H2O, the enthalpy of formation of this is minus 285.8 kilojoules per mole. That's the amount of energy that comes out of these gases when you make that, as we discussed above. So for 2 moles of H2 gas, we end up with 571.6 kilojoules per 2 mole, which ends up with exactly what was up here, minus 285.8 kilojoules per mole of H2 gas. Now we can get a ratio of how much energy went into making 1 mole of H2 gas and how much energy we get out when we burn 1 mole of H2 gas. So basically that's going to be the net difference of energy. So 111.6 plus a negative 285.8 kilojoules per mole, we end up with getting a net of negative 174.2 kilojoules per mole of hydrogen gas that we use. Now, I want to know what the energy density of water is if we were to be able to make this work somehow. So for 1 mole of H2O requires 2 moles of H2O to create it using this method of electrolysis, this hypothetical method of electrolysis. So we're going to convert to joules. So that's going back here. So that's minus 87.1 kilojoules for 1 mole of water. Now I want to see how many joules per kilogram of water, because that is the number that I have for gasoline, and I'm trying to compare it to gasoline. So we do this whole conversion equation. This is something everyone should be familiar with if you've taken Algebra 1 and physics or chemistry. So we just do the whole ratios of 18 grams in a mole, 1,000 grams in a kilogram, and 1,000 joules in a kilojoule. And we come out with 4.84 times 10 to the 6 joules per kilogram of water that we could extract out of the water. And then we pass the water on to the environment, and that's where we actually get the energy. So the hydroxide ions go on and they create some sort of reaction in the environment. So we're actually borrowing the energy before we actually burn the fuel, which is interesting. Now gasoline is obviously much more powerful, as you can see here. It's 47.0 times 10 to the 6 joules per kilogram of gasoline, and this is the higher heating value where all the vapor has condensed after burning it. So obviously, if we were to make this work, you couldn't get much out of it, but as you can see, there's actually some sort of potential if you could make that work. There may be some flaws in my reasoning here, but please go ahead and point them out if you can think of a way that we could make this work. I'm open to ideas, and this could be something great, or it could just be a little brainstorm. Anyway, thanks for looking.